Assalamu alaikum everyone. I'm Naila Asgar, and today we are going to explore one of the most extraordinary material in modern science, something that is lighter than air, stronger than steel by weight, and can withstand the heat of blowtorch. Yes, we are talking about nanoceramic aerogel, the solid smoke that's changing the world. Before digging into the main topic, I'm going to explain the simple analogy. Thinking of jelly, when you dry it, it shrinks and cracks. But what if you could remove the water without shrinking it? You had get a solid that mostly air, and that's the basic concept of aerogel. Firstly, here is the content breakdown, which covers certain points like from where and well aerogels are discovered, what aerogels basically are, why nanoceramics matter, their morphology and key properties, their mechanical revolution and keyword applications, and how do aerogels connect with SDGs. Here, firstly, is the abstract, which I am going to explain at the end of the presentation. And after abstract, there is a history to explain. History of nanoceramic gel include that nanoceramics is a advanced class of engineering. And imagine aerogels as incredibly ultralight material, often called frozen smoke, within history that reads like a story of forgotten invention, space age revival, and modern innovation. It is all started in 1930 when a curious chemist first created them. But they were mostly a laboratory novelty for decades. Then NASA stepped in. Needing a super insulating transparent material for space missions, they brought silica aerogels back to life, proving their worth in the vacuum of space. However, silica aerogels have limits, especially for extreme heat. This sparked a new wave of creativity where scientists engineered entirely new type of nanoceramic aerogels from tougher stuff like zirconia, making them far more resilient for high temperature jobs. Finally, in the modern era, the recipe got even better. Researchers began blending these ceramic sponges with polymers and super materials like graphene, making them stronger and more versatile. While new manufacturing techniques brought down the cost, today this journey from a lab experiment to a space age wonder has finally made aerogels practical, leading to their use in everything from advanced insulation and firefighting gears to energy devices and consumer products. In the PDF shown on screen, there is a history which is divided into four phases, which I explained now. And we are moving towards the introduction of the aerogels. Introduction of aerogels includes the information about that the evolution of material has increasingly moved towards the engineering of void, the deliberating design of internal space to achieve properties that are physically impossible in bulk solids. Nanoceramic gels represent the alternative manifestation of this paradigm, defined not by a specific chemical identity but by a unique structural morphology. Aerogels consist of a three-dimensional solid network of interconnected nanoparticles that typically occupy less than 5% of the total volume. Since their discovery in 1931, aerogels have transitioned from laboratory curiosities to the cornerstone of modern technology. Recently recognized by IOPEC as a top 10 emerging technology in chemistry for 2022. While traditional silica-based gels paved their way, the modern frontier lies in nanoceramic variants, oxides, nitrides, and carbides, which offers unprecedented thermal stability, mechanical resilience, and chemical functionality. And the define of nanoceramic gels is that they are the ultra lightweight, highly porous materials derived from gel where liquid components has been replaced with gas. resulting in a solid with a nanoscale network structure. The ceramic aspect refers to the composition offered based on the silica and other metals like alumina, which imparts high temperature stability, superior mechanical properties compared to the traditional silica aerogels. And there is a picture of aerogel shown there, a piece of air like trapped air particles. And the next topic I'm going to explain is the fundamental morphology and physical properties of nanoceramics. To understand nanoceramic aerogels, one can utilize the analogy of gelatin desert. When preparing, a gelatin powder is mixed with hot water and cooled until it's set into a wiggly gel. If the gel were simply dried in an oven, it would collapse in a teeny pile of powder. However, if a liquid could be removed while the solid shape remained intact, the result would be an aerogel, a structure that looks and feels like a solid but is mostly composed of air. On a microscopic level, these materials resembles a kitchen sponge, but while a sponge has many pores measured in millimeters, aerogel have pores million times smaller on a nanometer scale. And the next point is the nanoscale effect and porosity classification. Imagine aerogels as incredibly ultralight material called as frozen smoke. Their nanoscale effect is that a nanoceramic is a solid made almost entirely of tiny integrate air pockets with the actually solid material forming a web of nanoscale strands. Scientists classify these tiny air pocket pores by their size, and most of the pores in the aerogel are in the mesoporous range, too small to see but just the right size to trap air molecules very effectively. The structure of extremely tiny porous pores create what's called the nanoscale effect because the pathway for heat and sound to travel through are so narrow and twisted they get trapped, and that is why aerogels are such phenomenal insulators against both temperature and noise. In fact, they hold the record for the lowest thermal conductivity of any solid. Furthermore, the network is so full of air that aerogels are typically 80% to 99.8% empty space. This makes them incredibly light. Some are even dense than the air around us. It's this combination of being mostly air structured the nanoscale that gives aerogel their ghostly appearance and their super insulating lightweight properties. And the main point in this topic is the ray light scattering and optical characteristics, which shows the color of the aerogels. The blue color in many aerogels work exactly the same as the blue sky. When light enters the aerogel, it bumps into countless tiny nanoscale pores and particles that make up its structure. These features are small that they interact with light waves. They tend to scatter or deflect shorter light waves, which we see as blue and violet much more than longer light waves, which we see as yellow and red. This scattered blue light goes in all directions, giving the entire aerogel its characteristic blue glow when light shines on it. Meanwhile, the red and yellow light passes through more directly. That is why, if you look through a piece of aerogel towards the light source, is often paired with a yellowish or reddish tint. The blue light has been scattered out of the path to your eyes. In shorter, it is not a dye of pigment. It's the color comes purely from the physical interaction of light with the aerogel, incredibly fine structure. And now the point I'm going to explain is thermal transport mechanism, the Knudsen effect. Aerogels are the world best insulated because they cleverly block heat in three different ways. Imagine heat trying to travel through the material and hitting a series of perfect note roadblocks. The first point is the trapping air, the Knudsen effect. In normal insulation, light travels through a air to the trapped air as molecules bump into each other. In an aerogel, the pores are incredibly tiny, smaller than 50 nanometers, that air molecules cannot move freely. They constantly smack into the pore walls instead of each other, which stops them from effectively passing heat along. It is like trying to have a conversation in a narrow echoing hallway where you only hear your own voice bouncing back instead of talking directly to someone. And the second point is blocking the solid path. Heat also travels along the solid ceramic skeleton of the aerogel. However, the skeleton is a tangled, delicate web of nanoparticles with very few connection points. Heat must follow an extreme long, inefficient, and broken path, which drastically slow it down. Thinking of it as a highway filled with the dead ends and narrow footbridges instead of straight multi-lane road. And the third point is stopping invisible heat rays radiations. At high temperature, heat also travels an invisibly infrared radiation like the heat from hot oven. While some aerogels let these radiations through, advanced variants are mixed with special additives like carbon black and titanium dioxide that act as a sunscreen. These particles absorb or reflect the infrared rays, preventing this type of heat from passing through. By combining these three strategies, immobile air, creating a tortuous solid path, and blocking radiant heat, aerogels achieve their legendary super insulation with record low thermal conductivity. And the next point is molecular synthesis, that how aerogel is made or created. The process involved in this synthesis is the sol gel process. Sol gel process is a recipe for building an aerogel from the molecule up. Instead of carving a solid block, scientists mix liquid chemical building blocks like silicon or metal compounds to grow the material from scratch. Here, how it works, starting with a liquid soap, the sole. It begins with a liquid solution containing a special molecule that act like tiny construction pieces. Trigger the chemical reaction. When water is added, it break apart these molecules into in a step called hydrolysis, making them sticky. Building the network like gel. The sticky piece that start linking together in a process called condensation. They form bond like metal oxygen metal bridges, and they begin assembling into nanoscale particles. These particles further connect, creating a 3D web that spread throughout the entire liquid. At this point, it transforms from a free flowing liquid sol into a rigid wet gel that holds space shape. Sorry, imagine a very delicate waterlogged sponge at a molecular level. And the fourth step is strength and structure, like aging. The wet gel strong enough isn't strong enough yet. It is left to sit so the linking reaction can continue, which thicken the strands of the network and makes it sturdier. Sometimes extra additives are mixed in here to control final structure, strength, and structure. And the fifth point is to remove the liquid like drying. Finally, the liquid trap inside the pore is carefully removed. This must be done extremely gently to avoid collapsing the delicate nanoscale structure, which remains is what remains is a solid skeleton of aerogel filled with air. And the drying process is important. So Creating a aerogel delicate air-filled structure is the hardest part of the process. The final and critical step, which is drying. Removing the liquid from the wet gel without letting surface tension crush into teeny nanoscale pores. Imagine the solid network such as fragile sponge made of drinking straws. If you simply let the liquid evaporate, the surface tension at the liquid air boundary would create powerful inward forces collapsing all the straw. To avoid this, scientists use special drying methods that bypass this problem. And these methods are supercritical fluid extraction, freezing, freeze drying, ambient drying, and the first drying is supercritical, the gold standard. This method completely avoids liquid and gas phase. The wet gel is placed in a high pressure chamber and the liquid, often alcohol or liquid like CO2, is heated in a pressurized chamber until it becomes a supercritical fluid, a state where neither is a true liquid nor a gas. In this form, it can be gently vented away without ever creating a damaging liquid air boundary. This preserves the gel original nanostructure perfectly, producing the highest quality aerogels, but it is complex and expensive. The second drying method is freeze drying. The crystal work around here. The liquid in the gel is rapidly frozen solid. Then, under low pressure, the ice is turned directly into vapors, a process called sublimation. Skipping the liquid phase entirely, this avoids crushing surface tension, but there's a trade-off. As the ice crystal form, they can push solid network aside, creating larger pores. The result is often a slightly different material called a cryogel, which is still highly porous but may have different mechanical properties. And the third drying is ambient pressure drying, the chemical reinforcement approach. This is the more economical method for mass production. Before drying, the gel's internal space is chemically modified to make it water repellent. Then the liquid is carefully swept out for one with very low surface tension like hexane and slowly evaporated at normal pressure. While some shrinkage occurs, the pre-strengthening the network during aging step helps it withstand the mild capillary forces, resulting in a good through sliding denser aerogel. In short, the drawing frontier is all the outsmarting physics, either by eliminating surface tension entirely, avoiding liquid phase, or chemically reinforcing the structure to survive it, to preserve the miraculous air-filled nano architecture of aerogel. Now, here is the picture that shows the formation of aerogel, cryogel, and zerogel. And now I'm going to explain the types of aerogels. There are two basically types of aerogels, which is high temperature ceramics and non-oxide ceramics. The high temperature ceramic systems contain alumina and silica. Like regular silica gels are amazing insulators, but they have a limit. Like a snow fort in the cell in the sun, they start to shrink and collapse when things get hotter above 800 degrees Celsius. For instance, jet engines or spacecraft, the space that face extreme heat, we need a tougher material. That's why nanoceramic aerogels like alumina and zirconia come in. They are the heat resistant champions of aerogel family. And the first is alumina aerogels, the heat resistant shapeshifters. Their superpower is that they can potentially handle temperatures up to blistering 1800 degrees Celsius. The query is that as you heat it up, the internal crystal starts to change its phase like ice melting into water, but solid to solid. Each change causes the tiny particle to grow and snuggle closer together while reducing porosity and surface area. Scientists mix in a small amount of silica. Think of the silica as a nanoglue that forms bond between the alumina particles and holding the porous networks in place and preventing it from densifying too quickly. This keeps it strong, insulating at high temperature for longer time period. And the second type is zirconia aerogel, the strong but the brittle one. Their superpower is that there is their excellent insulation and chemical stability at high heat. The quid is that it has a major weakness. When heated or cooled, it undergoes sudden phase change that make it expand or shrink slightly. This create enormous stress, causing it to crack under turn to powder. To fix this problem, it always stabilized by mixing in another metal oxide like yttria. This yttria stabilizes zirconia. It's like giving the material a flexible skeleton, locking it into a stable crystal from that doesn't change violently with temperature prevented cracks. In short, alumina zirconia aerogels are the advanced heat-resistant upgrades to silica. Scientists engineers them with special dopants like silica for alumina, yttria for zirconia to overcome their natural tendency to collapse or crack, making them protect for the most demanding insulation jobs on Earth and in space. And their second type is non-oxide ceramics. Building on the heat-resisting oxide ceramic, scientists have developed an even more advanced class called nanoceramic oxide aerogels. They are made from compounds like boron nitride and silicon carbide, which brings a whole new set of superpowers to the table, especially for extreme environment. Here, a simple look of these cutting edge materials: nitride aerogels, the slippery stable sponge. What is this? Thinking of it as a ceramic cousin of graphite or graphene, its atoms are arranged in strong, slippery heat. Their key traits include extremely high resistant, like they stay stable in air up to 1300 degrees Celsius, super water repellent, hydrophobic. It's naturally heat waters. This make it perfect for soaking up oil and chemical spills from water, like a high-tech reusable sponge for environmental cleanup. Good electrical insulators don't doesn't conduct electricity, which is useful for electronics. How we made it. Often scientists start with the graphene aerogels as a template and chemically convert it into a boron nitride, preserving into a porous, lightweight structure. Silicon carbide aerogels, the tougher and the unusual controversist. What is this? An ultra tough ceramic known for being hard and resistant to wear, and now in the lightweight porous form. Their key traits are they are extremely durable, like more resistant to deformation under heat and harsh chemicals than silica. Astonishing antifoam, like some silicon carbide aerogels have the negative poisons ratio. This means that when you squeeze them, they contract inwards from all the side, in turn of bulging out. When stretched, they expand outwards. This bizarre behavior helps them to absorb suddenly massive temperature swings without cracking, like from 200 degrees Celsius to 900 degrees Celsius in seconds. And they are created by using a polymer drive ceramic method. You started with the silicone rich plastic foams, then bake it into a very high temperature. The plastic convert into a ceramic, leaving behind its porous shape. While oxide ceramics like lumina are great constant high heat, non-ceramic open doors for more specialized jobs like cleaning coils, peels, protecting components from rapid thermal shock, or acting as insulation in thermal corrosiveness or electric sensitivity. In the nutshell, these non-oxide aerogels push the limit of what's possible, combining the legendary lightness of aerogels with the world-class toughness, stability, and some truly unique physical behaviors for the challenging applications. And here comes the chemical revolution, like overcoming the little bit brittleness in the aerogels left behind. For a long time, the biggest flaw in the nanoceramic aerogels was that they are incredibly brittle, like a delicate piece of dried honeycomb that would turn to dust if squeezed. A single crack would shatter the entire structure. However, a mechanical revolution has solved this by completely redesigning their internal architecture. Scientists have tackled this in two brilliant ways. Firstly, they stopped building aerogels from tiny dots like nanoparticles and instead starting weaving them from long flexible ceramic nanofibers. Imagine the difference between a fragile towel of stacked marbles and a resilient springy mattress. These nanofiber aerogels can be compressed up to 95% and then spring back to shape because the fiber bend and buckles without breaking, distributing stress throughout the resilient network. And the second strategy is to create hybrid composites by infusing ceramic skeleton with tough polymers, like embedding a flexible net within a brittle structure. The most advanced method uses a double cross-link design inspired by a toughness of a biological tissue. This creates a sacrificial bond inside the material that breaks under stress and absorbs massive amount of energy, preventing a claw crack from spreading. This approach can make these aerogels nearly 50 times tougher than traditional little brittle predecessor. In short, by learning from nature and rethinking building blocks, scientists have transformed aerogels from a fragile novelty into durable, flexible, and resilient materials ready for real world uses. Thermal, the um, thermal energy storage is and here comes the applications which and the first application is the environmental remediation and resource recovery. The massive surface area and tunable chemistry of nanoceramic aerogels make them unparalleled as absorbents and filters for environmental protection. Uranium extraction from seawater and wastewater. As nuclear energy demands grow, extracting uranium from aquatic environments have become a priority. Aerogel-based adsorbents, particularly those modified with amidoxamine groups, have demonstrated extraordinary sorption capacities for hexavalent uranium. Their capacity, some aerogels reach capacities of 8.8 mole per kilogram. Their kinetics is that the graphene ambidoxamine hybrid aerogels can reach equilibrium in 1 hour, just in 1 hour, and maintain high reusability 87.3% after 10 cycles. And the process is generally endothermic and entropy driven, relying on the formation of inner sphere complexes between the uranyl cation and surface actin moieties like carbonyl and amino groups. And the second application is oil water separation and air purification. The super hydrophobic nature of boron nitride and silicon carbide aerogels allow them to selectively absorb oil and organic solvent from water sources with an uptake capacity of up to 1500%. Furthermore, aerogels can be used as filters for capturing heavy metal ions, for example, from industrial wastewater and gaseous pollutants like formaldehydes and carbon dioxide from atmosphere. And their third application is the aerospace cases of NASA. Aerospace remains the most demanding and prestigious application for nanoceramic aerogels, where their weight saving and insulating properties are critical for mission access. Like in Mars rovers experience extreme temperature fluctuation with nights ranging minus 10 degrees Celsius since the 97 Mars Pathfinder mission. NASA has used silica aerogels to insulate the electronics and batteries for rovers like Sojourner's Spirit and Opportunity. The aerogels provide a thermal barrier that prevents the rover from freezing during the Martian night while adding negligible mass to the spacecraft. And the third is Stardust mission capturing cosmic dust. In 1999, the Stardust spacecraft launched in with a specialized aerogel collector designed to capture particles from comet wild to comet dust travels at speeds up to 6 km per second, hitting a solid surface would vaporize particles. The silica aerogel functions as a soft landing medium. The particle enters the aerogel, leaving carrot-shaped tract as a granule is slowed down, allowing scientists to recover intact samples of primitive solar system matter for the first time. And their other application is energy storage and advanced electronics. The 3D interconnected nanoporous network of aerogels provide a massive surface area for electrochemical reactions, making them ideal for the next generation of energy storage devices, which is batteries and supercapacitor. Aerogels serve as carriers for electrode materials are electrolyte facilitating rapid lithium ion insertions and extractions. Metal organic frameworks derived graphene aerogels have maintained capacities of 1439 gram after 200 cycles. Aerogels regulated ion channels enable symmetric cells to operate for over 1400 RS with high Coulombic efficiency. The high supercapacitance electrical conductivity of carbon ceramic hybrid aerogels allow for energy storage densities for exceeding traditional electrolytic capacitor. And the other is thermal energy storage is a clever way to save heat for later use, and nanoceramic aerogels make it more efficient. Think of it as a high-tech thermal battery. Here's how it is work is that engineers use special materials called phase change materials, PCMs, substance like certain waxes and salts that store a huge amount of energy when they melt like ice melt, absorbing heat to become water. However, however, in a solid state, PCMs can leak and their heat can escape quickly. This is where aerogels comes in. Its role is twofold as a nanosponge and a super insulator. As a nanosponge, the aerogels porous structure act as a microscopic scaffold that soaks up and hold the liquid PCM in a space, preventing any leaks. And the second has a super insulator. The aerogels incredibly low thermal conductivity wraps around the stored heat drastically, slowing down its escape. This keeps the heat trapped right where you want it until you used it. This combination is especially useful for technologies like solar power systems where heat from the sun can be stored during the days and released at night, or in electric vehicle battery pack where it helps manage temperature and prevent dangerous overheating. And here is the most important point, the link of nanoceramic aerogels with SDGs. It links with primary, the link of nanoceramics with primary SDGs is that the SDGs number 7, which says that affordable and clean energy, and the SDG number 13, which is climate action. Drastic in the reduction in energy demand through super insulation. Their application is the building retrofits aerogels render improve insulation without adding bulk, cutting heat, cooling energies by 30 to 50%. Industrial efficiency, insulating pipelines and reactors reduce heat loss by 50 to 80% in sectors like LNG and chemicals. Renewable energy enhance thermal storage efficiency in concentrated solar powers and cryogenic tanks for hydrogen and ammonia. The SDG number 9, which is industry innovation and infrastructure. Their core contribution is that the lightweight, high performance material for advanced applications. Their application is that their lightweight composite used in aerospace and automotive to reduce weight and fuel use. Advanced sensors, integrated infrastructure for real-time health monitoring, for example, bridges, pipeline, catalyst port, high surface area and tunable porosity, optimize catalyst for CO2 conversion and green hydrogen production. SDGs number 12, which is responsible consumption and production. Their core contribution is longevity and functionality, sports, circular economic goal, and their application is durable insulation lifespan exceeds 50 years, reducing replacement cycles, captured nanoparticles, volatile organic compounds, and heavy metal oxide from exhaust streams, and to life focused research on recyclable and bio-based aerogels, for example, from rice husk ash to close the material loop. And it also minimally connects with secondary impacts of impact SDGs, which is like SDG number 33, good health and well-being. Hydrophobic aerogels prevent condensation and mold in building envelopes. Silica aerogels serve as controlled drug delivery systems and lightweight prosthetic components. And that's the number 6, which include that of clean water and sanitation. And the 14 SDG, which is life below water. Functionalized surface enables selective adsorption. Oil spill cleanup, oleophilic aerogels absorb 40 to 10% their weight in oil. Thiol amine modified aerogels chemically bind heavy metals like mercury, lead from water, and that's the number 11 and 15, which is sustainable cities and communities, which is aerogel based reflective roof coating, mitigated urban heat island effect, thin breathable aerogel panel, a low energy retrofits for of historic buildings without damaging aesthetic and structures. And the soil remediation like aerogel powders immobilize pesticides and hydrocarbons, preventing groundwater and contaminations. Now the topic is complete. I'm going to explain the abstract, the summary, and the conclusion of the topic, which is written here. Mm, Here, which includes Nanoceramics aerogels represent a remarkable fusion of material science and nanotechnology, transforming a once fragile laboratory curiosity into a versatile and high performance material, essentially for modern and future technologies. And as we know, nanoceramics is the advanced class of engineered material that is both extremely lightweight and highly porous, essentially a solid structure made mostly of air, with up to 99.8% of their volume consisting of empty space. They are created using precise chemical methods, primarily the sol gel process, which involves forming a wet gel that is then carefully dried using chemical techniques such as supercritical freeze and ambient pressure drying to prevent the delicate nanostructure from collapsing. The material excel at insulating against heat due to their nanopore structure will limit the movement of air molecules, a principle known as Knudsen effect, originally quite brittle. Newer form of nanoceramic aerogels has been developed to be more flexible and durable, incorporating nano oxide ceramics and nanofibers beyond important real Beyond their scientific interest, these aerogels have important real-world applications and support global sustainability effect, including environmental cleanup, improved energy and storage, and thermal insulation, contributing directly to survival. Several United Nations SDGs, such as clean water, affordable clean energy, and climate action, as we have studied earlier. Now, the story, and this is the end of the presentation. The story of nanoceramic aerogels is still being written. The next chapter will be authored by those who see not just what these materials are, but what they just could become. And with that, the presentation is ended.